Okay, so this is going to be page 76 and 77 of your notes. Now, I realize that there's a lot of words here. The words are important, and I need you to kind of look through them. I'm not going to say all of them. There's really only one main thing that I want you to get out of this lecture, and it's the idea of electrons having energy. And that's more towards the end of what I'm going to say here. However, I still want you to watch this whole video and look through these notes. Okay, so when scientists were developing this image of the atom, there was one sort of puzzling aspect of this picture. And it's the fact that we have protons inside of a center that are positive, and then we have these electrons that are outside of this nucleus that are negative. And scientists were kind of like, why doesn't the electrons, if they're attracted to the positively charged protons, kind of collapse on side of the nucleus? Okay. And this kind of has to deal with the idea that these electrons have more energy the further away from the nucleus they are. Now that may seem a little confusing at this point in time because we haven't talked about a few things. But I just want you to kind of realize that scientists developed a new image of the atom based on the fact of energy, based on where the electrons are located in relation to the positively charged centered nucleus, if that makes sense. You might want to rewind that and hear me say that again. Okay. So you learned in physical science, or you should have learned in physical science, about this idea of electromagnetic radiation, which is how we see light. Okay. And there's actually, if you remember that big long scale, right, you have radio waves all the way down to gamma waves. In the center somewhere is this really tiny spot where it's visible light, where you have your Roy G. Biv, right? Red, orange, yellow, etc. as the rainbow. And the reason why each color, or the reason why we can see each color, is because of the wavelength that is present for that specific color. Okay. So I've kind of just wrote here some wavelengths that you've seen on that scale before. Visible being the one where you see color. X-rays we can't see because, well, we use them to see bones, but it's actually a different form. It's not in that visible range. It's its own entity. Where we also have radio waves, which is going to have the highest wavelength. And gamma's not on here, but gamma actually has the smallest wavelength. Okay. Okay, electromagnetic radiation are forms of energy, right? If we have something that's moving as a wave, that wave is going to give off some sort of energy, okay? And then here I'm talking a little bit about frequency, and wavelength is equal to this thing called c, which is the speed is equal to the frequency times the wavelength. So the speed at which the wave moves is going to be equal to its frequency times wavelength. We're not going to do any calculations with these things. I just need you to see this to know that this is ultimately going to deal with energy, which I'm going to talk about here in a second. Okay, so the next thing I'm going to discuss is the atomic spectra. Okay. Now this is the important part. So I'm sorry, you can't even see it. When atoms absorb energy, electrons move into higher energy levels, meaning if I was to look at Bohr's idea of an atom, okay, so let's see here. Let me draw something simple like lithium. Okay, so lithium has 3 protons inside of its nucleus, and here's its first orbital. It has 2 electrons, and here's its third orbital with its 1 valence out in the top. Okay. This is the Bohr model for lithium. Okay, so what's going to happen here is when this electron goes up into the second orbital, it is actually going to be absorbing energy because the second orbital has more energy than the second one. Okay. Now what's going to happen is that electron doesn't want to stay there. We call this, when an electron moves from one energy level to the next, the excited state. Okay. Electrons don't really prefer to be in the excited state, so what's actually going to happen is that electron is going to move back down to where it originally was, which is called the ground state. Okay, so the electron is going to move back down to its orbital that it wants to be in, and that's called the ground state. Now let me ask you a question. If the electron, as it moves up to the excited state, absorbs energy, what is going to happen to that energy as it falls back down to the ground state? I hope you're thinking that it's going to have to release it somehow, and that's exactly what happens. Okay, so if I'm looking at this on a higher scale, so if the electron moves up to the excited state, it's going to absorb that energy, and we're going to call energy E. Okay, so the electron's now up here. And when that electron falls back down to the ground state, it's going to release it. Okay? And more specifically, it's going to release the energy in this thing called like a photon. Okay? And that equation is the energy is equal to h, which is a constant, which we're not going to talk about, times the frequency. Okay? So what's going to happen is when that electron absorbs the energy as it moves up from this low state to the high state, or the excited state, it's going to take in energy. Okay? But then the electron is going to move back down to its ground state, where it wants to be, right? And if it absorbed energy moving up, it must release it as it goes back down to ground. Okay, so if energy is being released as the electrons fall back down to the ground state and release some sort of photon, which we can call light, or somewhere on that electromagnetic spectrum, we can actually identify atoms based off of light wavelengths that they emit during the course of excitation of electrons. Okay, and that's kind of what this is telling us up here. It says light emitted from those atoms consist of a mixture of only specific frequencies. Okay, so for instance, you can't really see the colors here, but that's okay. Hydrogen will give off a photon or have some sort of frequency at 410 nanometers wavelength, 434 nanometers wavelength, 486 nanometers wavelength, and 656 nanometers wavelength. And that is very specific to hydrogen. No other atom will have this. Okay, because hydrogen's electron excitation is very specific to its atom. Okay, same thing with helium. Now, if you look at air, there's a bunch of different things here. If this was to be color, you wouldn't be able to see the difference between anything because we have tons of different types of atoms inside of air. And this is actually how scientists discovered what stars were made of, because they were able to look at the stars through telescopes and see these specific wavelengths, specifically for hydrogen and helium, because that's what stars are made of. Okay, so that is probably the most important thing that I want you to understand, is that when electrons are excited, they absorb energy. For when they fall back down to the ground state, they're going to release the energy, which then releases some sort of wavelength or frequency on the electromagnetic spectrum that we can then identify. Okay. This is also kind of just reinforcing what I just stated. So electron orbits, which is what Bohr said, are different energy levels, okay? And those electrons, he stated, will only follow a certain path, which each individual one is going to have a certain energy, okay? The energy of the electron is going to be greater the further away it is from the nucleus, so that's really important to understand. And then this is where it's talking about the ground state, which I already stated. Okay. One last thing about energy transitions is that these are going to be, transitions are going to be exact amounts, right? And we actually call them jumps. So you're not going to have a non-specific energy jump. They're most of the time are going to go up by like 1, 2, 3, 4, 5 energy level. Okay, there's not going to be like a 1.5 energy level or a 2.5 energy level. They'll be in very discrete jumps based off of where the electrons will be within the atom. So that's it for this video. Thank you.